Okay, so I noticed quite some confusion between all the right-hand rules used in the magnetism unit. So I thought I'd provide this video with a brief overview. And so I hope that this helps you to differentiate between the different right-hand rules. There's essentially three different types of right-hand rules to use to determine the direction of the magnetic force, to determine the direction of magnetic fields generated by currents, and to determine the direction of what we call area vectors. So I hope that you're able to apply the correct right-hand rule in each case. And so again, to stress this, there are a number of different right-hand rules that we use throughout this unit, but they all come down to three fundamentally different phenomena that we describe. The first one is there's a set of right-hand rules to tell us what the direction is of the magnetic force. And the origin in all those cases is the cross product. And so for the cross product, we need a right-hand rule, and that actually leads to the right-hand rules for the magnetic forces. An entirely different case is case B here, which is where we use the right-hand rules to essentially determine the direction of the magnetic fields that are generated by currents in a wire, a loop, or a solenoid. And so finally, there is a right-hand rule that we use to determine direction of area vectors, and I'll give some example of that as well. So if you can distinguish between those three cases, it becomes a lot easier to actually figure out which right-hand rule to use. So let's first focus on the first one. So we started actually by looking at what the force is on a moving charge in a uniform magnetic field. And so that's given by this magnetic force here, QV cross B. And so essentially that's just a cross product. So the direction of the force will be determined by the direction of the cross product modulo the sign of the charge here. And so this is how I think the right-hand rule for the cross product is most easily visualized. Point the fingers in the direction of the first vector, curl towards the second vector, and then your thumb points in the direction of the cross product. So V cross B means points in the direction of V, curl towards B, then your fingers point in the direction of V cross B. If your charge is positive, that will be the direction of the force. If your charge is negative, that will be opposing the direction of the force. So that right-hand rule is just directly from the cross product. Now we use that to then figure out what the force is on an entire current carrying wire. Okay, so if you have a conductor, the total force is now IL cross B. And again, this originates in the same cross product. And in fact, this is a cross product. It's written explicitly there. It's L cross B. Okay, so it's the same right-hand rule. In this case, the first vector is L, is a vector in the direction of the current. So fingers in the direction of the current, curl the fingers in the direction of B. Your thumb now points in the direction of the force. So it's the same origin in a cross product. Therefore, it's essentially the same right-hand rule, just the same as the force on a charge. So that's the first type of right-hand rules. The second set of right-hand rules relates to the direction of a magnetic field generated by currents in a wire, loop, or solenoid. And so I think it starts from this here. So if we have a single wire, okay, with a current flowing, in this case, upwards, we can predict what the direction is of the magnetic field. By this right-hand rule, you grab the wire, you point your thumb in the direction of the current, then your fingers curl in the direction of the magnetic field. Okay, as indicated here, current is up, thumb points up, your fingers curl in the direction of B. So B actually is always tangential to these concentric circles around your wire. That is essentially the origin for all the right-hand rules that relate current to a magnetic field somehow. Okay, and so this is really the one to understand and the one to memorize, and you can essentially derive all the other ones from this particular right-hand rule. So if you take that wire and you essentially bend it in the shape of this loop here, for instance, okay, at each point along the wire, you can use your right-hand rule. You can grab the wire, point your thumb in the direction of the current, and now your fingers will curl in the direction of the magnetic field. And so if you do that at all points along the wire, what you see is that it's always the case that the magnetic field on the inside of the loop is actually pointing up, right? That's from that first right-hand rule about the direction of the field if you just have a single current, okay, single current conducting wire, current carrying conductor. So for a loop, this means that your magnetic field essentially is going to look like this, okay? And so we get this from that same right-hand rule. You grab the wire in the direction, with the thumb in the direction of the current along all points on the wire. You see that at all points, the magnetic field is actually pointing up. So this is how you would draw the magnetic field line. Now, if you look at this in detail, there is actually perhaps a simpler way to figure out this direction. If you now consider the entire loop, you can actually describe this field with a different right-hand rule, right? You can now say like, well, let's curl our fingers in the direction of this current, then our thumb is actually pointing in the direction of the B field. Now, this may on first sight sound like it's a completely different right-hand rule, but actually it's not. It's the same situation, it's just a different description of that situation. If you only remember this right-hand rule for a single current carrying wire, right, where you grab the wire, point your thumb in the direction of the current, and your fingers curl in the direction of the magnetic field, you can work your way around what the field will be in a loop, just applying directly that right-hand rule. And so that's totally equivalent as using this right-hand rule. This perhaps is a bit easier to actually quickly figure out if you just need to know what the magnetic field is of a current loop. And so the same is actually true for a solenoid. So you build up a solenoid by essentially placing a lot of these current loops right next to each other. So you can use, again, the first right-hand rule that we had for magnetic fields of a wire. If at each point you put your, you grab the wire with the thumb in the direction of the current, if you do that at each point along this wire here, you'll always see that the magnetic field is pointing out. Like in this case, the current is going down, so it's pointing always to the right. Same here, the current is going down, magnetic field will always be pointing to the right, no matter where you actually grab that wire, okay? And so by doing it like this, you can actually figure out what the magnetic field is even in a solenoid, because here too, at each point in your wire, you can grab the wire with your thumb in the direction of the current, and that will actually have your fingers curl in the direction of the magnetic field. So you always find that the magnetic field, in this case, with the current going down like this, would point to the right here. And that's, again, totally equivalent as using this derived right-hand rule, where you now say like, well, if we curl the fingers in the direction of the current, our thumb is in the direction of the B field. That works for this current loop, but of course it also works for a solenoid. Why does it work? Because it's the same right-hand rule as we had before. Okay, and so they're totally equivalent. If you only remember the first one, you can always find back these other right-hand rules as well. This right-hand rule for current and loop related to magnetic field, that also works when we talk about the induced magnetic field, when we talk about magnetic induction, right? And so when we do that, we figure out there's an induced current, like in this case, the induced current is going clockwise. So again, you can grab the wire, point your thumb in the direction of the current, and now you'll see in this case, the magnetic field on the inside is always pointing down. And again, that's equivalent as the second way of saying this, that for a current loop, if you curl your fingers in the direction of the current, your thumb actually points in the direction of the B field. So here too, curl in the direction of the current and your thumb will actually point down, which is the direction of the B field. And so all these right-hand rules related to currents and magnetic field directions, they're essentially all the same thing. They all stem from this first one here, which is if you grab the wire with the thumb in the direction of the current, your fingers curl in the direction of the magnetic field. And now there's one more phenomenon that we've discussed, and that's related to area vectors, right? So if we have an area typically enclosed by a loop, for instance, we can define an area vector A, like we did for the magnetic dipole moment, right? So mu is I times this vector A, and this vector A is essentially a surface area vector. And so we say it's perpendicular to the surface area, but what's going to be its direction? It can go left or right. Well, so if we're talking about a current loop specifically, our right-hand rule is, well, curl your fingers in the direction of the current, then your thumb will point in the direction of that area vector A, which is also the direction of that magnetic dipole moment. Does that right-hand rule sound familiar? Well, it's exactly the same as the one we just derived for a current loop and the direction of the magnetic field, right? So before it was if the fingers curl in the direction of the current, the thumb points in the direction of the magnetic field. Now it's the same thing. The fingers curl in the direction of the current, the thumb points in the direction of that area vector. So that area vector actually points in the direction of the magnetic field that is generated by that current loop, okay? And so it's not a mystery. It's essentially the same right-hand rule as what we had before. But now, what if there is not necessarily a current running through? Well, and that's I think the last case that we encountered when we talked about magnetic flux, for instance. If there's no current running through, you can still define your area. And now you have two directions, upward or downward, for that area vector A. And you're like, how should we choose? And does it matter? There's no current going through this loop here. So how can we now figure out what direction to choose? And so we use the right-hand rule where essentially we defined a positive direction. We said, like, we'll just pick a direction, right? It's going to be up or down. Whatever it is, you point your thumb in the direction of that area vector that you picked. Then your fingers are going to curl in something that we call the positive direction. And if you do that and you work everything through consistently, then things work out all right. But I don't think you actually need to remember this right-hand rule. Okay, this is what we used to go from Faraday's law directly to figuring out what the direction is of the induced current for magnetic induction. And actually then we've seen Lenz's law is doing exactly the same thing, and Lenz's law is actually a lot easier to figure out in most cases. And so it doesn't even matter necessarily which direction you choose, because we also saw that the direction of the induced current is independent of our choice for the direction of that vector A. Okay, and so I think this right-hand rule, I think is probably not terribly important, and you can probably forget. The other ones, I hope by reducing them to essentially two different cases, that it makes it a bit easier to figure out which right-hand rule to use in what case. So I hope that's helpful.